Hello everyone, welcome to topic 5.2, Introduction to Rate Law. By the end of this, you should be able to represent experimental data with consistent rate law expression. This means that we will look at experimental methods that can be used to acquire data and how we can use math and proportional relationships to determine the rate law, which is a way for us to measure and express how fast or slow rates of reactions occur. So, since a rate of reaction can only be determined experimentally, we can use experimental data to write a rate law. A rate law describes how the rate of reaction is proportional to the concentration of each reactant raised to a power. So for example, we have D plus 2C yields AB. The rate law for this might, and that's the big thing, might be found experimentally to be rate is equal to K times the concentration of D to the 0th power times the concentration of C to the first power. And the big thing here is might. That means that this can vary. And it's temperature dependent, it's dependent upon what you're reacting, but you always have to do an experiment first. So this is a hypothetical situation that is not always true. The other thing, as a reminder for math skills, is that anything to the 0 power is actually just the number 1. In the rate law, we express it this way, so that way we can see that, and we'll see this later, that the concentration or the rate of this specific reaction is independent or not dependent upon the concentration of D. My apologies. So this reaction would be described as 0th power or 0th order with respect to D, and first order with respect to C. This means that if the concentration of D is changed in any way, it does not affect the rate of the reaction. Very few reactions are actually 0th power, but in this case, for hypothetical reasons, D is. If the concentration of C is changed, then the rate of reaction changes by the same power because it's first order. So if you double C, then the rate is doubled. If C is quadrupled, then the rate is quadrupled, and so on. The sum of these exponents describes the overall rate order. This reaction, in instance, would be first order because you could take 0 from the exponent for D plus the exponent from C, and that equals 1. So it is, first order. Where did that word go? First order. Note that the coefficients have not one thing to do with the rate law. The rate law can only be discovered by experiment. The constant K is different for each reaction and set of conditions. The value for K is dependent upon temperature. So, like, temperature is one of those things that affects rate law or the rate of reaction. So the K that you calculate is specific for one temperature. So if we change the temperature, that changes the overall rate of reactions for everything, and thus K changes. This is known as the rate constant. So K is your rate constant. You will often be asked to solve for this value and provide units. The units for K describe the overall reaction order. So based off of the reaction order, you will have very specific units for K. Okay, the ones that the AP test primarily focus on are for 0, first, and second for all rate law expressions. However, it has been popped up on rare occasions where we see rate orders or reaction orders higher than second. So it's good to know those and to be able to look at them and understand what's going on. Okay, and the best way to figure out the units for K is to actually just plug it in and solve it. Comparing the initial rates of each individual reactant allows us to determine how each reactant affects the rate of reaction. We can then write a rate law for the reaction. This is also often known as the method of initial rates. So finding the initial rates of reaction based off of concentrations altering one or both concentrations multiple times and seeing how the rate of reaction initially changes. We can then use the comparative values for those, as shown in this example here, to determine the rate law and determine the rate order. Okay. So looking at the data, we can see that there are 2 experiments with the same values for A and 2 experiments with the same values for B. The concentration is held constant when they have the same values. So if we hold A constant, we can expect the data. When A is constant, as in experiments 1 and 2, we see that we double the concentration of B. And so when we then look at the initial rates, we see that the rate, so if we multiply these by 2, we see that this is doubled as well. This tells us that the reaction is first order with respect to B. Okay, because when one doubles, the other doubles. So if we're looking at the nth power and it has to equal whatever's happening over here, n has to be 1 in order for that to be true, so that tells us it's first order. When we look at B being held constant here, and we check this is being multiplied by 3, so tripled, we look at then what happens here, and we see that that is going up by a factor of 9. Okay, so that tells us that for this one, 3 squared is equal to 9. And so that tells us that it is second order because the squared, you have to square however you manipulate the concentrations to get the change in the initial rates, and so that tells you second order. So the overall rate law then is rate is equal to K times A squared times B, and that the overall reaction order is 2 plus 1, which gives you third, or 3, which is third order. We can then solve for the value of K, which is important if we were to look at other experiments and predict, hey, how's the concentration going to affect, how's our reaction rate going to affect. So plugging in, and you can use any set of initial conditions, but it's usually just best practice to use the first one up here, so experiment 1. Substituting in the values, you end up with this answer. So we plug in the initial concentration of A and B, my apologies, from experiment 1. And this works for any, but it's easiest if you just do this one. And then when units cancel, you end up with 1 over meters squared times seconds, or not meters, molarity squared, or molarity to the negative second power if you pulled it to the top, times seconds to the negative first power, because it's in the denominator. When you pull it to the numerator, it flips. More than one variable changes. It's a little trickier to determine by inspection. You can compare 2 experiments using this expression, and it doesn't always have to be experiment 2 divided by experiment 1. It can be any combination of 2 experiments as long as it fits. Looking at this data in this data table, we see that there are no experiments with the same value for A, but there are for B. So we see here we have two that are the same for B, so we can compare these two. So this is being multiplied by 4, so we look over here and we see that this is multiplied by 4. So we know that it is first order with respect to A. We can then use that to figure out the order for B. And so looking at the reaction order for B, the easiest one is probably going to be looking at experiment 1 and experiment 3. Okay. And because the numbers are nice and we probably will get a whole number relationship. So setting it up so that the experiments are a whole number. So you put the bigger number on top, divided by the smaller number for the rate, and then you follow the same pattern. So setting up the 2 rate law expressions for experiment 3 and experiment 1. So K, and this should actually be K3 because it's from experiment 3. K3 over K1 times the concentration of A from experiment 3 and experiment 1, to the first power, because we know it's first order, times the concentration of B from the experiment 3 divided by experiment 1 to the n power. This is our unknown, and we're going to try and solve for it. And that work is shown here. So simplifying, you end up with 2 here. This becomes 2 times 2 to the m is equal to 4. And simplify stuff, because you can't combine those two bases. You divide both sides by 2. And this cancels, and so you're left with 2 is equal to 2 to the m, and so thus m has to be 1. The numbers should work out to be very, very straightforward. You will not see any non-whole number first order, or any non-whole number reaction orders. You're not going to see half or third order. It's beyond the scope of the class. Okay. This reaction is then first order with respect to B as well. So you write this overall rate law, which then tells you the overall reaction order is 2 or second order. You can then solve for K by plugging in any set of initial conditions. In this one, to kind of point it out, you are actually using the third experiment here data, and it'll give you the same for that set of initial conditions, it'll give you the same K values, the same pressure, same temperature. Okay, so looking at this I do, we're going to practice this concept together. Okay, so the easiest is to, when it says what's the reaction order with respect to CO, is to look at the other reactant and see where it's constant. So it's constant here. So I want to see how this is changing when I go from one to the other. How are these changing? And it's actually easiest to go from 3 to 2 and see going from, oops, my apologies, can't draw today. 3 to 2, we see that we multiply this by 4. Okay, so that tells us that we are quadrupling the concentration. And then we're going to look at how does this one change going this direction. So 2.1 to 8.4, that is also being multiplied by 4. So that's 4 to the nth power. What does n have to be for this statement to be true? N has to be 1. So this is first order. And for the most part, a lot of these will follow this pattern where you can use the data to simply find them. I believe there may be practice problems where you have to, I'm looking through the answer key. There are none, there is one, number 6, where you have to use the example as shown here, to find it. So number 6, this is going to be like number 6 in your UDO. But most of them should be able to be worked out this way. Okay. So then what is the reaction order with respect to NO? So I could switch pen color, but I just erased it. So for NO, we want to look at where is CO, or NO3, where's CO, or carbon monoxide, constant. So that's experiment 1 and 2. So we're going to go from the smaller to the bigger. So we see that that is multiplied by 2. So we're going to check how does this change. And you can use a calculator. Pay attention to the exponent. Okay, we see that this is going from 0.0084 to 0.0168. We see that that is multiplied by 2. So we have 2 from our concentration is equal to 2 to the nth power from our initial rates. And then for this one, then n has to be 1. So that tells us it is first order for NO3. So our overall reaction order, we would add these two together. So 1 first order from the carbon monoxide and first order from the nitrogen trioxide tells us that the overall reaction order is 2. So it is second order overall. Okay. Then the overall rate, or the rate law, which is our equation for this, is rate is equal to K, the rate constant, times the concentration of our first reaction, or reactant, to the first power, and our second reactant to the first power, because they're both first order. Now, because it's the first or power of 1, you do not have to write those, but I like to write them so it reminds me that it's not 0 order, that it does impact. But you don't have to, okay, because it's mathematically not necessary. So what is the value for K? We can use any one of the experiments, but I'm going to just use the first one. So the rate from the first one is 1.68 times 10 to the negative second molarity per second. Units are very important for the K value. And then times K is equal to K times the initial concentration of carbon monoxide, and that's to the first power, times the initial concentration of the nitrogen trioxide, forgot my units, to the first power. Solving this for K, you should get 1.68, because you're going to divide by your concentrations, times 10 to the negative second molarity per second, divided by 0.120 molar times 0.720 molar. This molarity cancels this one, and plugging it into the calculator, you should get 0.194. In molarities in the bottom, so you could either say 1 per molarity second. I don't like saying that because this 1 looks like it's supposed to be part of this number, and it's not. So I like to say inverse molarity, or molarity to the negative 1 power, second to the negative 1. And if it was squared in the denominator, it's to the negative second. And that's backwards. Okay, so let's look at the we do. In the we do, consider the reaction 2 NaOCl gas yields 2 nitrous oxide plus chlorine gas. Consider the rate law that shows it is a bimolecular reaction, so it gives us the rate law. So that means it's probably, sorry, I was going to say 0 order to another reactant. There is no other reactant. Woo! When the initial concentration of NaOCl is 0.391 molar, the rate is 9.32 times 10 to the negative third molarity per second. Find the value with K with units. So we're just going to substitute in our rate and the concentration into the equation given. So rate is 9.32 times 10 to the negative third molarity per second is equal to K times 0.391 molarity squared. Rearranging for K and solving for K, you should end up, so K, if you rearrange, is 9.32 times 10 to the negative second molarity per second divided by 0.391 molarity squared. This tells us that you're going to have units of molarity to the negative 1 times seconds to the negative 1. And your answer should be 0.0245 molarity. Nope, that's the answer for the next one. My apologies. That's special. 0.0610 molarity. That's the correct answer. I'm sorry. Okay, so then what will the rate of reaction be if you change the concentration to 0.634 molar? Now that's not a clean double, so we can't just double or quadruple the rate because it's second order. So you actually have to plug in the number. So rate is our unknown because that's what it's asking us for, is equal to K, which we just calculated, and it's going to be the same as long as all the other initial conditions are the same, temperature, right? K stays the same as long as temperature is, and we can assume it is because it's not telling us that it isn't. So we have K times the concentration squared, so 0.634 molar squared. Okay? And so that should give you 0.0245. And the units, molarity -1, seconds -1 times molarity squared, this cancels and this becomes 1, so it's molarity per second, which actually works out for the typical rate units, amount per time. Okay, so using these concepts, you are going to solve these rate law questions in the UDO. Check your work online, and thank you for tuning in.